binary search, merge sort, quicksort. 3 lessons, 3 algorithms, and if you line them up, they are the same move in 3 costumes. Binary search split the array at the middle and threw half away. Merge sort split at the middle and trusted both halves. Quicksort split around a pivot and recursed on the sides. Split, recurse, put the answer together. You have been using one of the most famous ideas in computer science for 3 lessons without being told its name. Today it gets the name divide and conquer. And more importantly, it gets a price tag you can read at a glance. Because last lesson ended on a promise. Log in levels in work per level showed up twice in 2 different algorithms, and the arithmetic came out identical both times. That was not a coincidence. There is a way to read the cost of any algorithm shaped like this straight off the shape of its recursion. No algebra. That skill is the centerpiece of today. The template has 3 beats. Divide. Split the input into smaller pieces, usually halves. Conquer. Solve each piece with a recursive call, the leap of faith from 2 lessons back. Combine. Assemble the piece's answers into the whole answer. Now hold each algorithm up to the template, because the differences are where the insight lives. Merge sort is the textbook fit. Divide at the middle, cheap. Conquer both halves. Combine with the merge, one linear pass where all the real work happens. Quicksort plays the beats in a different order. The partition does the real work first. Small things left, big things right. So when the 2 sides come back sorted, there is nothing left to combine. The combine was prepaid. And binary search is the degenerate case, in the best way. It divides at the middle, but one comparison proves the answer cannot be in one of the halves. So it conquers one half and abandons the other. No combine at all. The answer just bubbles up. Recurse on both halves, pay a combine. Recurse on one, pay almost nothing. Keep that distinction in view. It is about to become the entire cost story. Here is the pricing trick, and it fits in one sentence. Draw the recursion tree, and the total cost is the work per level times the number of levels. That's it. That's the skill. Start with binary search. One call does a constant amount of work, one comparison, then recurses on half. So the tree is not really a tree, it's a chain. In, then in over 2, then in over 4, down to 1. How many levels? However many times you can have in. Log in. About 20 for 1,000,000 elements, 30 for 1,000,000,000. Work per level? Constant. One comparison. So, constant work times log in levels. Order log in. The price you derived in Lesson 8 by counting halvings now reads straight off the shape. One branch, cheap levels. The levels alone set the price. Now merge sort. Both halves plus a linear combine. The tree is the full picture from last lesson. In at the root, 2 halves, 4 quarters, down to single elements. Billet level by level. The root merges in elements, in work. The next level, 2 merges of in over 2 each. Add them up. In again. 4 merges of in over 4. Still in. Every level moves the same in elements through merges. The tree is flat. So, in work per level times log in levels. In log in. Read off the shape in 5 seconds. No sums, no induction. And quicksort with good pivots is the same picture from the other direction. Each level partitions in elements total across its calls, log in levels deep. The tree does not care whether the linear work happens before the recursion or after. 2 branches with linear work gives a flat tree, and a flat tree always bills in log in. That rung from Lesson 1's ladder is not a formula to memorize. It's a shape you recognize on sight. One more shape, because not every tree is flat. Suppose splitting is cheap, but combining costs n squared. The root bills n squared. The next level, 2 combines of half size, square the half, double it, and the level bills n squared over 2. The next, n squared over 4. Each level costs half the one above, and Lesson 1's doubling sum, run in reverse, says the whole tower adds up to at most twice the root. The root dominates. Total, order n squared, and the recursion underneath it was noise. Now flip it. If the work per level grows as you go down, the leaves dominate, and the total is just count the leaves. So every recursion tree tells one of three stories. Top-heavy, the root pays. Flat, multiply by log n. Bottom-heavy, count the leaves. There is a formula that mechanizes this. It's called the master theorem, and it is honest reference material. Look it up when you meet a recurrence in the wild. But it is exactly these three stories with the cases labeled. Levels times work per level. That one move prices nearly everything in this course. Time to use the paradigm on something new, not just relabel old wins. Here's the problem. An array of numbers, some negative. Find the contiguous stretch with the largest sum. Say, -2, 1, -3, 4, -1, 2, 1, -5, 4. Somewhere in there hides the best run. Brute force tries every stretch, every start, every end, sum each one. That's the quadratic triangle again, dead at scale. So think like the last three lessons. Split the array at the middle. The best stretch now lives in exactly one of three places. Entirely in the left half, which is the same problem, smaller, recursive call. Entirely in the right half, recursive call, the leap of faith covers both, or lying across the middle, 1 foot on each side. That third case is the only new work we have to do, the combine.
The crossing case looks hard until you notice what crossing means. The stretch touches the middle boundary, so it must be the best suffix of the left half glued to the best prefix of the right half. And each of those is one scan. Walk left from the boundary, running sum, remember the best. -1, +4, 3. -3, back to 0, +1, 1. -2, -1. Best suffix, 3. The stretch 4, -1. Now walk right from the boundary. 2, +1, 3. -5, -2. +4, 2. Best prefix, 3. The stretch 2, 1. Glue them. 3 + 3, 6. And look at what got glued. 4, -1, 2, 1. The recursion hands back the other two zones. Best inside the left half, 4. Best inside the right, 4. Max of the three zones, 6. Now price the whole thing without running it. 2 recursive calls on halves, and the 2 scans together touch each element once. A linear combine. You have seen this tree. It's merge sort's tree. Flat, n log n. So divide and conquer just turned a quadratic problem into n log n. And for a while, that was the best anyone knew. The problem comes from pattern detection in digitized images. Uwe Grenander posed it, John Bentley carried it around as a programming pearl. Then Jay Kadane, a statistician at Carnegie Mellon, heard it in a seminar and sketched, reportedly in under a minute, a plain loop that beats the recursion. 1 pass, 2 numbers. The best stretch ending exactly here, and the best stretch seen anywhere. At each element, the best stretch ending here either extends the previous one or starts fresh at this element, whichever is bigger. Update the global best. Done. Order in, constant space, no recursion at all. Sit with what just happened. The recursive solution was not wasted. It proved the quadratic was beatable, and its crossing scan is quietly load-bearing inside Kadane's loop. But divide and conquer is a design tool, not a guarantee of optimality. Sometimes the recursion is the stepping stone, and a one-pass loop is standing at the top. Why the loop is always safe belongs to the patterns course, under the name dynamic programming. Here, it's the punchline. Now, the story that made this paradigm famous, because it didn't just speed up a function, it broke a conjecture. Moscow, 1960. Andrei Kolmogorov, one of the great mathematicians of the century, runs a seminar and states a belief. Multiplying two n-digit numbers the schoolbook way costs n squared. And n squared, he conjectures, is optimal. In the audience sits a 23-year-old student, Anatoly Karatsuba. Within a week, he has a counterexample. Split each number into a high half and a low half. The schoolbook product needs 4 multiplications of those halves. Karatsuba found an algebra trick that recovers the same answer from 3. A bottom-heavy tree, but a thinner one. Count the leaves, and the cost drops to about n to the 1.58. The conjecture was dead, and Kolmogorov himself wrote the result up for publication. The descendants of that week are working for you right now. Python quietly switches to Karatsuba once your integers pass about 70 digits. The big number libraries inside cryptography, multiplying 2,000-bit numbers to open a secure connection, carry the same lineage. 1 seminar, 1 student, 1 week. 2 more things before the module closes. First, what the shape buys beyond speed, parallelism, nearly free. Merge sort's 2 halves share nothing. No memory in common, no coordination. Independent subproblems can run on different cores, then 4, then 8. Stretch the idea to its limit and you get MapReduce, Google's 2004 framework and the Hadoop and Spark lineage after it. Divide a job across thousands of machines, conquer the pieces, combine in a reduced step. Data center scale, same 3 beats. Second, the honest list of when it loses. If the subproblems overlap, the tree lies to you. Lesson 9's Fibonacci recursed on overlapping inputs and recomputed the same answers exponentially many times. The fix, remembering answers, is dynamic programming. The patterns course owns it. If the combine costs too much, a top-heavy tree just bills its root, and the recursion bought nothing. And if the problem does not shrink geometrically, quicksort on sorted input, peeling 1 element per call. You don't have divide and conquer at all. You have a loop wearing its costume. And that closes the module. 3 lessons ago, recursion was magic. Now the machinery is open. A call is a frame. Depth is memory. Writing a recursive solution is 2 decisions, a base case and 1 trusted step. And pricing 1 is a glance at the tree. Levels times work per level. You can write the recursive sorts and build them on site. That was this module's whole promise. Kept. Next, a new module, and a structure this course has owed you since day 1. Back in lesson 1, I asked you to file something away, a structure whose average case is order 1, whose worst case is order n, and whose entire engineering story is making that worst case so rare you can price it at the average. Time to take it off the file. Hash tables. How any key becomes an array index, what happens when 2 keys collide, and why every hash table you have ever used occasionally stops to rebuild itself. That's next.